When working with species data or other observations, it can be useful to know how the features are clustered or dispersed across the study area. For instance, you might want to know whether the spatial pattern is random or whether there is an underlying process driving a non-random pattern in the data that might warrant more investigation. Two techniques that are often used in GIS to study these patterns are Ripley's K function and the kernel density estimator. Ripley's K function is a tool that can help us determine whether or not points are clustered, random, or dispersed across the study area. The function is based on the number of points occurring within a given distance of a focal point. If the average number of points within the search radius is greater than what we would expect if the points were randomly distributed, then the points are considered clustered. If the number of points within the search radius is less than what we would expect, then the points are considered dispersed. We often want to know whether points are dispersed or clustered because it can lead us to investigate what processes are driving the patterns. For instance, if we are studying the prevalence of cancer in a community, we might want to know if the individuals with cancer are all spatially clustered together, perhaps in the same neighborhood, which could indicate an environmental source might be causing the illnesses. In conservation, we might want to know whether trees of the same species are clustered together in a forest, which might raise their susceptibility to disease. As mentioned, Ripley's K gives a good indication of whether or not the data are clustered or dispersed, but it does not tell us where that clustering is occurring. If we need to know explicitly where the clusters are located, then a kernel density estimation is a good choice. The kernel density tool calculates the density of features in a neighborhood around each point and creates a raster surface that represents the density of observations across the study area. Conceptually, the kernel density estimator works by fitting a kernel over each observation point. You can think of the kernel like a little bell covering the point, with the peak of the bell directly over the point and the height of the bell decreasing to 0 at a certain distance away from the point. Points that are close in space will have their bells overlapping. And if we were to sum up the height of all of the overlapping bells at each location in the study area, that would create a density surface representing areas where there were more observations and areas where there are fewer observations. The size or width of this kernel is defined by the user and is sometimes called the bandwidth. Adjusting this bandwidth will change the result. If you increase the bandwidth, the surface will become smoother. Ultimately, there is no universally correct bandwidth, so it's best to choose something that is grounded in your knowledge of whatever it is you are investigating. For example, if you were analyzing the kernel density of chimpanzees in Western Africa, you might choose a bandwidth based on how far that species is able to move in a day or how big their home range is. Kernel density surfaces are useful because they provide a spatial output of hotspots of observations. This map shows the density of whooping crane sightings in the winter of 1982 to 1983 around Aransas National Wildlife Refuge in southeastern Texas, USA. There is a hotspot of crane activity along the eastern coast of the mainland and another hotspot across the channel on the barrier island called Matagorda Island. Once we know where these hotspots are located, we can investigate what might be driving the cranes to these areas and use that information to better protect this endangered species. So to recap, it is often useful to measure whether or not features are clustered or dispersed in the study area, and also where those clusters are located. There are lots of spatial analysis techniques that can be used for these purposes, and we went over two. The Ripley's K function to look at whether or not features are clustered, and the kernel density estimator, which can show us where those features are clustered in the study area.